Just another 10 seconds before we get started. Okay. So, Unit 6, sinusoidal functions. So we talked about trigonometry, we talked about SOHCAHTOA, we talked about sine law, we talked about cosine law, how to find angles, how to find lengths. But one thing you have to realize is like, well, what does sine, cosine, and tangent even mean? Like we use them in a calculator. How do you even find values for that, right? We just kind of type it in. We're like, yeah, this is how you do it. But at the end of the day, the question is, how do calculators even figure out those values? Well, how do those values work? And so chapter 6 dives into the details of essentially what are sinusoidal functions, what are these functions, because sine, cos, and tan aren't just buttons. They're not just regular buttons. They're not variables. They're functions. And so as a result, as is the course here, as we talk about functions, what does a sine function look like? What does a cos function look like? Uh, Tan function we won't dive too much into this course, but cos and sine are the two focal points of our current unit for this one here. So there's a couple of important terms that you need to know. If you need to write this down somewhere elsewhere, like to practice and memorize, it's good for you to know. So the first term is called periodic, and periodic is something that happens or appears at regular intervals. And so it repeats multiple times, kind of like if we were to think about like a slinky, like an old slinky. If we were to drop it while holding on to it, it bounces up and down, up and down, up and down. It's a constant repeating motion. That special word to say that it's repeating is called periodic. So that's a special term that we're working on here about what is periodic, what does that have to do with anything, is because the functions that we're working on are going to be periodic. So they're going to repeat, they're going to have these cycles, these patterns that you're going to be able to identify. The peak and the trough. So this is just special words. So peak is the highest and trough is the lowest. In English, that's literally what they mean. Like the peak of a mountain is the highest point, the trough of a mountain is the lowest. Or you can consider, some people call, instead of trough, they call it a valley, because the valley is like the in-between gap between a mountainous range and not, right? So the peak and the trough are the two words. So peak is the highest point and the trough is the lowest point. And then the period is how long it takes for that repeating section to happen. So like if I was to record, like, for example, if this pen here was going from left to right and then back to left as one cycle, then how long did it take to complete that one cycle? Or if I were to put it in zoomer terms that you guys are, if you were to do record a boomerang on Instagram, how long it takes for the boomerang to repeat is one period. Does that make sense? I hope that's more clear. Okay. So the boomerang is the periodic motion, right? Boomerang is a periodic repeating cycle, and then the period is how long it takes for that boomerang to repeat. So that's now that I think about it, that's much better for you guys to remember. And then a cycle is essentially the boomerang itself, right? What is it that's being repeated? So uh, when you have when you record a boomerang and you do a motion, whatever it is, that motion is itself is the cycle. The time it takes for that motion to complete is the period, and the whole thing as a whole is called periodic. The boomerang itself is called periodic. Perfect. So those are the terminologies. You're going to hear me repeat these multiple times throughout this unit. So just make sure you're familiar with it. And if no one should ask me, Mr. Choi, what was that again? What is this again? When you're working with me, at least the way I teach, you should have these terms nearby so that you can look back at it multiple times, right? You should be able to look back and understand what it means. And then in the end, after all of that, you still really don't know, then you can ask me. But make sure you're still, I want you to get used to taking the time yourself to answer your own question, and then once you can't do that, then figure it out. Like the amount of times I have people asking me questions that you can Google drives me nuts. I don't know. For some reason, some people can't Google properly. Googling properly is a skill. I tell you that. I'm telling you right now. Googling properly is a skill. Okay. So, recalling. In grade 9, you had distance time diagrams, right? Motion diagrams. So, what does it mean? What does it look like if the person is running away? What does it mean if the person is going closer? What does it mean like if the person's not moving, right? Except we did this with linear graphs, right? Like, oh, the person is running to the store. You have a steep slope towards the store, and then the person is at the store. It's a flat horizontal line, and then the person walks back home. It's a less steep slope going all the way back to zero, right? You've done this kind of thing with linear graphs in grade 9 where you represent distance and time and speed on a graph, right? So when we repeat, if we were to repeat that motion, let's say the person does that every single day. If we were to copy and paste that motion all the way through, then we would get something that's periodic, right? And so we talked about like in grade 9, the steepness of the line represents speed. The furthest away is the location. Sorry, excuse me, so on and so forth, right? And continuing onwards from there. So, in page 326 of the textbook, they actually show you something like this, which is the moon phases that we view on the Earth. So, if we look at the day of the year versus when is the moon visible, so on and so forth, we get these cycles. So we have, of course, new moon, quarter, half, full, half, quarter, and then new moon, right? When you look at this, right, and you're trying to understand this process here, we want to look at these, and if I were to ask you like generally, hey, what's the period here? Approximately how long is a period here? Would anyone like to take a guess on how long the period would be? How long does it take? Not 74 days. 74 days would be everything. But the period only covers one cycle. So look at the. Sorry, repeat. Sorry. Amir, did you say 15?
Yeah.
No, not 15. 15 would not be a full cycle. You're like halfway there.
30.
30 is closer. 30 is much closer. Yes.
25.
It would be around the 25-30 range. The correct answer would be 28, 29. And the reason why we know that is, for example, on day 1, it tells us that you can barely see the moon, and that this is technically called a new moon. So outside, if you were to look at the moon, this is called a new moon. And the reason why it's called a new moon is because, well, the moon is not visible. And then the full moon here, when you see the moon completely, is halfway through the cycle. And once you get to here, this is back to new moon phase here. So obviously it's not exactly 0.00 here, but this from here, day 1 to 29, would be approximately one cycle that repeats. And you'll see, again, we repeat it all the way to 29 is around 30 days. You see that? So 29 to 59, another 30 days. And so we start seeing this cycle here. It's approximately 28 to 30 days, depending on, right, what we've seen so far. So the first thing was, right, it's not this whole section, not everything, all of the data is one cycle. The period is specifically only asking for what's the section that's actually repeating. So first we need to identify where's my section that repeats, and then from there, how long does that take? So Amir had an idea where he reached up to here. He's like, this is a full cycle. which is close but not quite because it doesn't repeat from new moon. So a cycle will have to end where it started. Does that make sense? So if it starts at a new moon, it has to end on a new moon. So here, the full cycle would be from here to here because that's the next new moon. And of course, if we were to keep filling in our information here, another cycle would be from the new moon here to the new moon here. Or I could do the cycle as, oh, I'm going to start from the full moon and go until the full moon, which is another 30 days, right? That works too, because the start and the finish are the same, right? So a cycle, depending on where you look at it, as long as it starts and ends at the same point, it's good. You're fine, right? And you'll notice the period should be exactly the same because it's repeating. It's 30 days regardless of where you start, as long as you're looking at a full cycle. So it doesn't matter where the cycle is, the period is always going to be the same. So that's really important information that we want to work with here as we, dive into this unit. So let's continue onwards here. If we were to graph this, right? So if we were to graph this table of data, this is what the graph would look like. We have our points here. And now visually representing it, this might be a little bit easier to identify what the period would be. Where's that repeating cycle, right? So the repeating cycle, you'll notice, is this section here. So if I were to mark it in black, it's this section. See how that constantly repeats? It goes up and down, up and down, up and down, up and down, right? It keeps going up and down, up and down, up and down, up and down. That would be a repeating section. If we only got halfway to 15, it would be this section, and we would have to see that section repeating over and over and over again, which we don't. The full section that repeats is this section cutting off, and you can copy and paste that, and you'll get the same thing, right? So it's when you start plotting it, when you visually see it on a graph, it's much easier to identify, oh, I can see what the period is, right? I can see where it starts and where it ends. So not only can you see it repeating there, what if you said, oh, another way I can see the repeating pattern is, oh, the highest point is here, and the highest point happens again over here. So this section is repeating, which is true. You can see that is also repeating. And this is what I mean by finding a cycle, where as long as you pick a correct cycle where it starts and ends at the correct position, that could be your cycle. And the period will be exactly the same. And here it says it's 30 days. As we predicted earlier, it's 30 days. The curve looks the same as the previous part, right? The next part of the curve looks the same as the previous part, right? And then this person decided to extend this graph, repeating that pattern over and over and over again. And then you can guess and estimate what it would look like 130 days later, for example. So this is just an example of using data, using something that repeats like the moon phases. And if I were to ask you like, oh, what's the moon gonna be like 60 days down the road? Like, what if it's like 21 days later? Is it gonna be a full moon, half moon? Do you know? And then if you were a scientist that knew, right, then you would say, yeah, oh, yeah, it would be, a partial half moon or something like that, right? Because you know that this pattern is consistently repeating, you're able to estimate now using that idea of periodic, right? Knowing that the moon's phases is periodic, you can estimate, right? And this goes for not just the moon, but a variety of different things in real life too, right? If, for example, something that you don't even realize happens at periodically are things like sports, right? Things like school, right? Something that repeats regular repeating patterns. If I were to ask someone who's a sports fan, yo, when does the NBA playoffs start every year? Right? That person doesn't even question like when it happens. It's a set date every year. It repeats every year, right? It's around this time. Yeah, I can approximately guess like it's gonna happen around here, so on and so forth, right? These are little things that we kind of don't think about it in a mathematical context, but then when we start breaking down, it's like, oh, we just naturally know how to do this. That's exactly why your calendar has full moon, new moons, stuff like that, and that's called the lunar calendar. So, why does it make sense to call the graph of the moon data a periodic function? Because the phases of the moon follow a repeating cycle with a period of 30 days. So we know exactly how long it takes for that cycle to repeat, and it keeps doing that over and over and over again. Okay, so that's what we're doing. Okay, let's continue onwards here. So let's say we're given here an example of a graph. This is the motion of a chopping machine. I don't know what it's chopping. You can imagine it yourself, whether you're looking at slap chop or an industrial chopping machine, your choice. Um, what is the period here? So I want you to think about it. Don't say it out loud. I want you to try solving these three, A, B, and C at least. A, B, and C, I'd like you to try it yourself, right? Take some time now. I'm gonna give you quick like 1.5 minutes. Quickly answer. What is the period? What's the maximum height? What's the minimum height? So once you have that down, then we're going to continue onwards. Okay. Hopefully you are finished. Anyone want to take a stab at what the period is here?
Is it 2?
2, and what's the units?
Seconds or centimeters? No,
Seconds. That is right. Seconds is right. 2 seconds is the period. So when I ask you what the period is, we're looking at the x values here, right? 2 seconds is the period. How can you find that? Usually it's the question. Well, I can draw this point. Hey, I'm going to pick the point after the dip, the highest point, and then we look for after the dip, the highest point. That is 2, and that is 4. Right? Oh, 2 to 4, 2 seconds. You could do lowest part as well, but that's a little bit harder to read because it's not really on the starting point. So see how that works? So it's like, oh, I'm going to pick these 2 points. Yep, that's 2 seconds there, so on and so forth. Or I can be like, oh, I'm going to pick the start before the dip and the start before the dip. And even then will be exactly 2 seconds. So regardless of where you see the cycle, no matter where the cycle starts, that repeating cycle is always going to be 2 seconds. That's the period. The maximum height, Rena typed it in chat for me. She DM'd it to me. Was 2 centimeters. And the minimum height, anyone?
0 centimeters.
Yes, 0 centimeters, right? So the highest point, which is 2, and the lowest point, which is 0. And we're looking at the y value here, which is in centimeters. Perfect. And these are, oh, this did not transfer properly, huh? That did not transfer properly. I'm trying to look at what happened with that translation there. Give me 1 second, guys. I think these are supposed to be numbers, but yeah, okay. I see what happened. Sorry, it's supposed to be 2 and 3. It's mentioning 2 and 3, and this is supposed to be 4. Sorry. And you can actually cross that out. Let's just talk about these ones here. Sorry. Really bad edit. So what is the meaning of the horizontal lines 2 and 3? So this section here and this section here, what does that mean in context of this question? What does that mean? Well, it means that the blade is resting at 2 centimeters, i.e. not chopping, right? And what does it mean for the V shape? Anyone want to take a shot at it? What does the V shape mean?
It's cutting the meat at 0 centimeters.
Yes, the blade is coming down to chop whatever it is and going back up. Right? The chopping, i.e. the chopping motion. Okay. So that's what those two shapes means. It's going and then comes back up, right? Slams down, comes back up, rests there until the next piece, and then keeps going in a repeating pattern. So that's what this context is here. So are you able to identify, these things where you look at a graph, I can figure out, oh, what's my period? What's the peak? What's the trough? What does this graph even represent at certain points within the context? Okay, so that's everything like that idea of what we're going to be working on here. Okay. And that's it. So the basic summary is that a periodic function is a function whose values are repeated at equal intervals of your independent variable, which is our x variable. So as long as it's repeating and it has a period, it is a periodic function. So that's what we're working on here. So let's take a look at some of the questions here, right? So question 1, 2, 5 to 7, and 9. Let's take a look at like question 1 and 2 here. So from your textbook here, A, B, and C. Is A a periodic function? Yes or no? Don't say it out loud. I'm gonna put a poll using the Are You Ready poll. Actually, I'll use the Is This a Function poll, but yes or no? Is this periodic? Yes or no? 1A. Shouldn't take too long. 5, 4, 3, 2, 1, 0. Nice. Most people said, yes, this is definitely a periodic function. It is repeating, right? It goes up and then down. And then once it comes back to the middle, that's one cycle. Up, down, comes back to the middle, second cycle. Very good. 1b, is it a function, a periodic function or not? 1b. Five, 4, 3, 2, 1, 0. Done deal. That is a function. That is a periodic function. It repeats. It goes down, up, stop, down, up, stop, down, up, stop, And even though some people are probably thinking, oh, that doesn't finish off here, just assume that it continues on. It will be a periodic function. Next, part C. Periodic function or not? 3, 2, 1, go. All right. Good. Most people said no, or not most people. Everybody said no, which is true. This doesn't repeat at all. It's a circle, right? It doesn't really repeat. If we saw multiple circles, then sure. But plus, it's not even a function. This is not a function. This is a relation. So very good for those that caught on to that. Let's move on into question 5 here. So let's do question 5 together, which is part of your homework here. Question 5. The graph shows an amount of water used by an automatic dishwasher as a function of time. And so it shows you a graph. The volume of water is on the left. Time in minutes is on the right. And so the first question is, why does the operation of the dishwater model a periodic function? And let's just jump right into it, which is part B. What's the period?
Is it 3 minutes?
Period is not 3 minutes. That would be way too short.
8 minutes.
No, 8 minutes, still too short.
13.
15 is correct. 15 minutes is what you're looking for. 15 minutes. So if we take a look here, it's kind of hard to tell from the beginning. You're like, I don't know what that looks like here. So let's say we start from, for example, let's start from like right up here, right? And if we see that repeating pattern happen here, we have to hit all the way past here. And you'll see also in the pattern here, you can go from the bottom V. So where's the V? Oh, the V starts at 8 minutes. Okay, let's see if that repeats. Where does that V repeat? We go all the way across, and the V happens again at 23 minutes. Oh, so from 8 to 23 is one cycle. It happens once, which means from 8 to 23, that's 15 minutes. It takes 15 minutes for this to repeat. And then you'll notice, oh, that means from 0 to 15, that's a repeating motion. Oh, it does do that. It repeats, and that same pattern seems to repeat twice all the way to 30 minutes. So the period here would be 15 minutes. And what does it mean for one complete cycle? I'm sure it just means that that's how much water it takes for a dishwasher to complete one set of dishes, for example, right? It takes 15 minutes to complete one set of dishes. Would be a good example or good explanation for one cycle, right? Maybe it goes through a hard wash and then a soft wash. I'm not entirely sure how dishwashers fully work. But I can assume that the 2-minute break is to fill in and pull out dishes and fill in dishes, maybe, right? For 5D, how much water is used if the dishwasher runs through 8 complete cycles? That's a very good question. How much water is used if the dishwasher runs through 8 complete cycles? Any ideas?
120 liters, maybe?
And how did you get that?
I did 15 times 8 because isn't 15 minutes one cycle?
It is 15 minutes for one cycle. How much water is being used within those 15 minutes? How did you find that? You just did 15 times 8?
Yeah, and also if you see the maximum, it's also 15 liters.
Right. So one thing you want to be careful about, that is a very good start there, which is I'm going to take the area, essentially just do a 15 times 8 and then just do that. But the thing here we want to be careful about is this is the volume of water being used, right, within the minute, right? So how much water are we actually using within 15 minutes is first what we want to figure out here. And then multiply that by 8. Does that make sense? So we want to figure out within one cycle how much water is actually being used. It's not just 15, right? If it's 15, if we're using 15 like liters of water for 1 minute, that's 15 liters in 1 minute. And so on and so forth. And we have to kind of fill in. Oh, wait, we can't just leave it there. We got a lot more to do. The way you can calculate this is figuring out the area underneath the graph. So when it asks you how much water is actually being used, it would be the area underneath the graph. So, and then you multiply by 8, like what Sydney says, because it's 8 cycles. So here, although some of you are like, Mr. Choi, you can't estimate what's underneath the graph. This isn't a rectangle or anything like that. I'm like, well, if you take from 0 to 13 and you kind of put the triangles and the parts that are like leaning out of it, you can actually make a rectangle from 0 to 13. So I actually do 13 times 15 and then times 8. So 13 minutes times 15 liters every minute and then times 8 cycles would be 1,560 liters of water. Okay. Now, what's really important for me here, we haven't done this in a very long time, which is 5e. What is the domain and range of our function? Okay, so I'm going to open up Microsoft Word here. Give me 1 second. So it's asking us, what is the domain and range for this? Okay, what is the domain and range for this function here? Anyone want to give this a shot? It's been a very long time.
Isn't it like the XER and YER?
Yep. So we have XER. Is there a restriction for X? Anyone?
Would it be 30?
30 would be the upper limit. What's the lower limit?
15.
Not 15.
0?
0, where it starts at. So it actually looks like this. Okay, so now we're diving back into domain and range. The restriction here, I'm going to state it. I wanted you to try it, which was XER. That doesn't change. Notice how this section doesn't change, right? X is any real number, but X has to be greater than or equal to 0, but less than or equal to 30. The way we do that is using two less than or equal to signs. We put our lower part, X can't be any lower than 0, and X can't be any higher than 30 within our graph, right? And so those are going to be our two ranges here as a result. Okay? So we want to see in context of like application problems and like graphs that have an end, we want to think where's our where's our lowest point and where's our highest point, and that's going to be our range. And so for this one here, people kept mentioning for y, oh, the highest point is 15, the lowest point is 0, which means you should be able to figure out the range. Y is any real number such that 0 is less than or equal to y, which is less than or equal to 15, the highest one there. So this would be the domain and range for this function, where y is any number between 0, can be any number between 0 and 15. Okay. And of course, we will get more practice with this with future questions as well. Are there any specific questions from people about today's lesson? That's pretty much it. That's 6.2. There's not much more to it. And tomorrow we'll be working on 6.3. All right, which means there are no questions here. I'm going to end the live stream there.